Hello and welcome back to our another session of the MII Measurement in Industries. I am your course instructor Motion Pandya, and this course is for semester 5 IC under GT. In the previous session, we did with the optical transducers, basically two types, and we are going ahead with the time of flight sensors, confocal sensors, and anthropometric sensors. In the previous session, we saw intensity-based sensors and our triangulation sensors. So let us start with the time of flight sensors. Here, once again, the word tells us about the flight timing. So once again, optical transducer is there. So we will be sending some light rays and we will be receiving them on the detector. Here, mostly we will be using IR kind of light source, and that is the electromagnetic wave, which is sent over the object, as you see in the diagram, and the time taken for traveling by the wave will be calculated here. Here you see in the wave that blue color wave is IR emitted, that is sent, and received, that is reflected by red color is shown. So distance is given by one-way time flight multiplied by the speed of light, which is somewhere around 343 meters per second. This one of the commercially available device I have shown in the picture, and the fraction of light that's scattered to the sensor will be little bit bigger than the source. Hence, a very sensitive detector and signal averaging is required in case of time of flight sensors. Time of flight measurement systems are based on the IR light, as I said, or in few cases visible also. And with the help of development of laser LED in the semiconductor technology, it has helped a lot to the time of flight kind of sensors developed in the compact systems. This one of the device I am showing you is OPT3101. It is an AFE, and basically it measures the phase, but the entire system combines with the light emitter and photodiode to make a fully functional system. It's taken from the Tensors instrument, and AFE is analog front end. Here it represents the portion which is related to the phase measurement. Phase representation to the distance of the target. Let me show you the previous slide where we saw this phase difference. Here you see the waveform, the red wave and blue wave, they have a phase difference based on the distance, and that phase difference will help us to detect the distance of the object. Let us go back to the slide. So this OPT is from Tensors instrument, one of the commercially available sensor that you can remember as a part of your practical knowledge in this. Next is confocal sensor. So confocal sensor is actually we will be using focused light, and apart that's the narrow part of the object in which you can detect the light and you can detect the distance. So here focused light from an aperture onto the object is applied. As you see in the diagram, you see lenses, beam and target. So here we will be using chromatic light, the amount of light returning to the illuminating aperture that varies with the object position. And accurate measurement of the displacement and surface profile at the distance of millimeters, if these both have your requirement, then confocal sensors are very much useful. Here we will be having two types. The one is monochromatic, another is polychromatic confocal sensor. So in monochromatic confocal sensor, we will be using monochromatic light, yani single wavelength, and that you see in the diagram with the theta angle, it is sent and through the lens again from the object at the from say distance a plus z and coming back, and it is detected, and it is actually operated in a closed loop employing the feedback mechanism. So very sharp measurement can be done, and it ensures the sensor is positioned to receive the maximum signal from the object. So you have to keep your the aperture which is emitting light in such a way that the maximum signal is received. In case of polychromatic, almost the system is same, but here not only one wavelength, it will be multiple wavelength of light, and I say highly broadband source is used here. We are using red and green, both colors are shown here to show the multiple wavelength. And different wavelength components at the different longitudinal positions on the object, that will be making you a very sharp image when the distance is to be detected. And in the region of image plane, each point has a different wavelength, and with a specific wavelength for each image point, it gives you much more better result. So here let us see one of the confocal sensor available in the market from the micro emulsion. I have got it for you here. So multiple lens systems are employed. You see 1, 2, 3, 4, 5, 6, 7 lenses are there, and then monochromatic light is generated at the different wavelengths, and you must remember that low reflectivity will be giving you low signal to noise ratio, and so signal to noise ratio should be higher in order to reduce the noise. Resolution will be depending upon the magnitude of the chromatic dispersion, and commercially available sensors are in say tens of kilohertz frequency burst. Here you see the frequency which was shown, like the object is moving near and away from your light source, and it depends on the focal length. So starting from the 1 mm to the several tens of millimeters. So basically this is for a very small displacement distance measurement system to be employed here. The next is anthropometric sensors. There are two terms associated with this that you should remember, that low current source is used, and white light instrument is known as WLI. These are the commercial terminology that you should remember. White light interferometric WLI, and in biomedical applications, optical coherence tomography (OCT), where they use a coherent laser to measure sub-wavelength. Sub-wavelength means the nanometer range displacement of an object, and it is actually appropriate for the displacement monitoring rather than to measure the absolute distance. Okay. Coherence length is the propagation distance over which a wave, coherent wave, let's say electromagnetic wave, maintains a specified degree of coherence. And here we will be talking about the interference of the waves. So that's why the name has come to the anthropometric sensor. Wave interference is stronger when the path taken by all the interfering waves differ by less than the coherence length. Okay. So by using this fundamental technique, we will be measuring the displacement here, or we will be basically monitoring the change in the displacement. Here you see low coherence source and reticle are shown, and one fiber coupler is given, collimators are there. So one reference mirror is created, one reference surface will be there, and another is the object. So reference mirror will be fixed, and on the basis of object variation, you will be able to get an image. Now, path difference of the two arms is greater than the coherence length. Here you see we have two arms, like the one is on the reference mirror, another on the object. And if the path difference is greater than the coherence length, then there will be no variation in the total output. So there will be no change in the distance. And with the same arrangement, if the path difference is less than the source coherence length, a typical sinusoidal variation will be measured in the output, and this will actually tell you what is the displacement change. Basically, this is more, as I said earlier, that not for the absolute measurement of the displacement, but if object is moving, then we have to detect the position and the change in the displacement distance, like say in some medical application. If we talk about the tumor detection, the position of the tumor, and certain biological particle movement that can be detected. Now, the specific type of interferometer, that is FPI, family parallel interferometer, or known as Adler. This is one of the IMP topic for GPU, specifically armed in the paper. So we will be looking into this also. Family parallel interferometer, which was invented in 1899 by Charles Fabry and Albert Perron. And Ethelbert comes from the French language, that measuring gauge or measuring standards. Here I show you one specimen of the device. Looks very complex. So we will be looking into the basic theory of this. So here we will be having laser, we will be having lens which is concentrating, and we will be having two mirrors with the silver coating, and from the object is at the distance d and with angle theta. So now what happens here? This device is called interferometer when the distance between two surfaces can be changed. Here I am talking about the two surfaces that parallelly you can see there, and that small d that you have to detect. Capital D will remain fixed. So here it makes use of multiple reflections of rays. I will be showing you one single ray. It will be reflecting between the two surfaces, a silver surface. So you see here that incident light at the angle alpha and the small distance d. The glass plates or silver plated plates are there, and the reflections are measured on the detector. Okay, that may be a digital detector, or it may be an analog detector. The M shows the order of the reflection, that M, M+1, M+2, M+3, etc. And here the path of the light is transmitted each time, and the light reaches to the second surface, resulting in a multiple offset beams that is interfering with each other. Here I have shown only one ray. Like multiple rays or large number of interfering rays will produce extremely high resolution. Here you see that at the alpha angle in the first diagram, at the angle alpha, and the second diagram, that one, angle alpha, with the rays that are reflected and internally they are interfering, and then they are making one image, and the path length difference can be calculated by using 2AB minus CD is equal to 2B cos alpha, where small d, that is our impedance area that we have to measure. And with the formula 2D cos alpha is equal to m lambda, where lambda is the wavelength, we will be able to measure the distance, small distance d, where one of the plate is fixed, another plate is moved along with the object. So reflection angle and the value of AB and CD here will be changed, and this way we will be able to measure the value of small d. This is heavily parallel interferometer FTI, and here we finish our topic on the optical transducers. We had gone through the 5 types of optical transducers. The first is intensity based, second was triangulation based. It was in the previous session. In this session, we have gone through time of flight. We have gone through another 2 types, and so these are the topics that we should cover under the optical transducer and displacement measurement. In the next session, we will be meeting with the another displacement measuring technique. Thank you very much.